Now, I'd like to begin my presentation. The title is Evolutionary Process of One-Year Fruiting and Two-Year Fruiting in genus Quercus. Fagaceae has a unique characteristic called delayed fertilization. This delayed fertilization is a phenomenon that takes several weeks to a year from pollination to fertilization. This feature is common in gymnosperms, but rare in angiosperms. Depending on the length of delayed fertilization, the species can be divided into two patterns, one-year fruiting and two-year fruiting. In case of one-year fruiting species, pollination occurs in the spring. Fertilization is delayed for a few weeks to a month. Fertilization occurs in late spring to summer, and fruiting occurs in autumn. So, one-year fruiting species bear acorns in the same year as flowering. On the other hand, in the case of two-year fruiting species, pollination occurs in the spring. Fertilization is delayed for a few months to a year. Fertilization occurs and fruiting occurs in autumn in next year. So, two-year fruiting species bear acorns in the next year of flowering. Basically, in Fagaceae, one-year fruiting or two-year fruiting is mostly determined by the genus. For example, Fagaceae distributed in China, all species of genus Castanea are one-year fruiting, and about 80% species of genus Castanopsis are two-year fruiting. However, genus Quercus is different. Half of its species are one-year fruiting and half are two-year fruiting. From this, we hypothesized that one-year fruiting and two-year fruiting trait in genus Quercus may now be in the process of evolution. To know about this, we are studying the question, which is the ancestral trait of the genus Quercus, one-year fruiting or two-year fruiting? Next is method. First, from the paper published by Mr. Hip in 2019, we obtained phylogenetic trees using 253 species in genus Quercus. Next, we investigated whether each of the 253 species is one-year fruiting or two-year fruiting. We used databases such as Oaks of the World, Flora of China, and Flora of North America, and then confirmed the trait with specimens from Kew Herbarium and other sources. Third, we reconstructed a phylogenetic tree excluding species for which there is no information about one-year fruiting or two-year fruiting. The details of the phylogenetic tree are explained in the next slide. Then we estimated ancestral trait and transition probability using Bayes trait. This transition probability is the probability of one-year fruiting changing to two-year fruiting and two-year fruiting changing to one-year fruiting. Original phylogenetic trees used 253 species, but after excluding species, the phylogenetic trees was reconstructed using 207 species. In phylogenetic tree figure in left, Next to the section name and main distribution areas, there is the number of species used in each section per the number of all species in each section. From this, we see that section Cyclobalnopsis is used by only 33 of the total 99 species, and its usage rate is about 37%. On the other hand, North American species such as in section Lobata and section Protobalanus have a higher usage rate than section include Asian species. Therefore, it should be noted that there is a bias in the used number of species in different sections. The result of ancestral trait estimation indicates that ancestral traits of genus Quercus are more likely to be 2-year fruiting. The probability that the ancestral trait was 1-year fruiting is 0.35, while the probability that ancestral trait was 2-year fruiting is 0.65. And transition probability were calculated, and there are 4 cases. 1-year fruiting remained unchanged. 1-year fruiting changed to 2-year fruiting. 2-year fruiting remained unchanged. And 2-year fruiting changed to 1-year fruiting. What we should focus on is the case of change trait. In the 1-year fruiting species, 69.3% species changed from 1-year fruiting to 2-year fruiting. And in the 2-year fruiting species, 92.8% species changed from 2-year fruiting to 1-year fruiting. This indicates that 2-year fruiting species were more likely to change to 1-year fruiting species. Let's go to discussion part. First, we will discuss the result that ancestral trait of genus Quercus are more likely to be 2-year fruiting. The reasons for this result are: 1. The relatively recently diverged section Quercus contains many 1-year fruiting species. Here is section Quercus. There are so many 1-year fruiting species. And the second reason is older branches, for example, Rhizocarpus and other outgroups, have many 2-year fruiting species. Here is outgroups. From these 2 reasons, we recognize that our future task is to reconstruct phylogenetic trees with more DNA data from species distributed in Asia, especially section Cyclobalnopsis, to improve the accuracy of estimating ancestral trait and transition probability. The result that the transition probability from 2-year fruiting to 1-year fruiting is higher indicates that the change from 2-year fruiting to 1-year fruiting is likely to occur. And we hypothesized on this question that this is because 1-year fruiting trait was created by the loss or change in the function of the genes that control the 2-year fruiting trait. And as a candidate of the function, we consider induction of fertilization after prolonged cold. So, what are the specific candidates for genes encoding induction of fertilization after prolonged cold? The first candidate is the genes associated with successful fertilization. We observed the expression levels of the genes SEC5A and SEC15B throughout 2 years. And these genes encode the subunit of the exercised, which is evolutionary conserved heterooligomeric protein complex. We found that both genes take their peak expression level in winter. The second candidate is a gene that encodes for the growth of ovule. This picture showed the ovule's cross-section of Lithocarpus edris. Lithocarpus edris is 2-year fruiting species. These photos show the ovules still immature as of November, matures in March to May, and fertilization is complete in June. In other words, the ovule is immature before winter, but maturation may begin when it experiences winter. These are 2 candidates that I am considering, but I feel that winter is key in both cases. Therefore, I think that winter might be necessary for the induction of ovule development and fertilization. That concludes my presentation. Thank you very much.